Okay.
I'm Paul Weiss, coming to you from Los Angeles through Beijing for today's ICANX talk. I'm the faculty at UCLA and the editor-in-chief of ACS Nano, and representing the ICANX team of Professor Alice Zhang of BEDA and Professor Chinapati Jagadish of ANU. I'll be your host today, and we have a terrific lineup for July, so please do come back every Friday. And today, we're delighted to have Professor Aditi Sarma speaking, and I'll introduce our panelists and challenger after his talk. So, Professor Aditi Sarma is the inaugural holder of the J.N. Tata Chair at the Indian Institute of Science in Bangalore. His research focuses on strongly correlated electron systems, semiconductor nanocrystals, and energy materials. He's a fellow of all three science academies and the Engineering Academy in India, as well as TWAS and the APS. He's received a very large number of awards and honorary degrees. He's also an editor of our sister journal, ACS Energy Letters. We're delighted to have him giving today's ICANX lecture on chemically exfoliated lithium disulfide. And Professor Sarma, the floor is yours.
Thank you, Paul Weiss. Let me share my screen. I start with thanking the ICANX team, in particular Jagdish and Paul, for this kind invitation so that I can share some of our excitement working in this particular area for the last 3-4 years. And particularly to Professor Paul Weiss, it's very early in the morning for him, I know, and I really deeply appreciate, because I know how difficult it is to get up so early in the morning and to attend. And also to the other panelists, Professor Lee, Dr. Govindan, and the other panelists, Roy also. What I'm going to talk today, as the title says, is the two-dimensional MoS2, and we'll try to see what we understand of its properties. That's a very broad statement. Let me redefine the scope of the talk today. What I'm going to talk about is, for reasons, just a second, it looks like for some reason it's not changing. Okay, with the laser pointer, I'm not getting the changer. So what I'm going to do is to use the cursor to draw your attention.
Oh, I'm afraid you're muted.
I'm muted. Okay. Can you hear me now?
You just muted right after they used the cursor rather than the laser pointer.
Okay. Sorry. Okay. Oh. So I'm going to redefine the scope of the talk a little to tell you what to expect from this talk. What we have is MoS2, that is going to be the only compound that I'm going to talk about. Of course, it's a bulk material, but it's a layered material. So you can get a few layers of MoS2 separated, exfoliated in many different ways. And this particular method of exfoliation that we're going to talk about today is going to be the, I don't understand, okay, is going to be the chemical exfoliation technique. And I'll tell you a little bit about it. And it so turns out, and I'll show you along the line, that when you chemically exfoliate, something strange happens to MoS2. Its properties change drastically, and it's believed that MoS2, when you chemically exfoliate, gives rise to some kind of metastable state, which is somewhat elusive precisely because it's metastable. It doesn't last for very long. It can stabilize it for some time, but there's been a lot of controversy trying to understand its properties. So what we are going to do is the main thrust of the talk going to be is to try and understand the origin of this metastable state and what is the nature of this metastable state. That is the idea for today's talk and the scope of today's talk. Before I tell you about it, let me also acknowledge the support, financial support that I have received rather generously from various agencies in India, in particular Nanomission and ACRB, through Department of Science and Technology, Government of India. And there's a private funding, Jamshedji Tata Trust, that I was very privileged to have over the last 3 years. They funded our past research in recent times very, very generously. So let's get to I don't have to impress on you why two-dimensional systems are exciting. Ever since graphene happened to the world, everybody's been excited. But then we figured out that graphene is not the only two-dimensional system with exceptional properties. There's a whole slew of compounds that you can form in two-dimensional way. For example, boron nitrates, carbon nitrides, metal dichalcogenides, silicene, MgBt. So to provide you the context of what I'm talking about today, in this whole zoo of two-dimensional systems, what we're going to pick out is this very subspecies, so to speak, of metal dichalcogenides today. Clearly, that there's a metal and there's dichalcogen in it, such that essentially the entire class of this metal dichalcogenides can be thought of having a layer of metal atoms here in the central layer with 2 layers of chalcogen on top and below, which could be sulfur, selenium, or tellurium. And that forms a nice layer which is separated from the next layer by a van der Waals gap. So they're generally naturally layered compounds stacked one on top of the other by the van der Waals interaction between the layers. This metal dichalcogenide also comes in very many different colors, so to speak, in the sense that depending on which metal you're talking about, the properties are drastically different. For example, if you're looking at vanadium disulfide, choose the metal to be vanadium, it's known to be a metal. If you look at tungsten or molybdenum as the metal dichalcogenide, then what you get is a semiconductor, and you can make electronic units, transistors out of it. If you change the metal into niobium and choose your chalcogen to be selenium, then niobium diselenide is a superconductor. You can have tantalum disulfide, which is a charge density wave system, which shows transitions from one phase to the other as a function of temperature. So there's a plethora of properties that is possible, and obviously we're not going to talk about all of them. So we have to focus our mind down in the metal dichalcogenides into one system. And the system that I've chosen for today's talk is molybdenum disulfide. The molybdenum disulfide itself is actually presents us with a variety of properties. If you look at the molybdenum disulfide, and the operational word that I want to focus on is the bulk, as you will get a piece of molybdenum disulfide. It's a semiconductor. It's a large band gap semiconductor, and it has an indirect band gap. Imagine that this layered compound whose bulk you're looking at, and it's an indirect band gap semiconductor, a large band gap. You take one layer out and study its property. It turns out that a single layer would still be a large band gap, but instead of being an indirect band gap semiconductor, it will become a direct band gap semiconductor. Not only that, of course, for making any devices, we need not taking out one layer, I need many, 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 many layers. And the popular approach to getting many layers, instead of doing a mechanical exfoliation one layer at a time, there are many different ways of creating, exfoliating a bulk MoS2 such that it gives you many, many layers, many layered compound. And that's a chemical exfoliation method. And that chemical exfoliation method has been found that you can use this chemically exfoliated MoS2 to put together in devices, for example, supercapacitor. Here is a plot of showing, it's too small maybe for you, so let me read out. And the x-axis is the power density. On the y-axis is the energy density. And of course, one wants in any kind of energy storage material to maximize both power density and energy density, which means that you want to move up along the diagonal line to get the best device. And it has been shown that with this chemically exfoliated MoS2, you can go up there in this particular paper. It's up there showing that in this, you have extraordinary properties of MoS2 that you can get out of that. It's also been claimed that they are very good for hydrogen evolution reactions. So to keep in mind, this is the insulating form, very large band gap, which are obtained from the bulk or mechanically exfoliated system. And this is the part which is the chemically exfoliated. And this is the part where all the devices are being made are believed to be, generally believed to be the metallic T form. So there's a sharp contrast between the bulk and the mechanically exfoliated one, which gives rise to mainly a wide band gap insulator with a crystal structure of H form. The chemically exfoliated ones, because of very drastically different properties, was believed to give rise to metallic and T form crystallography. Now, why did that happen? How does that come about? In fact, this is one paper that we had ourselves published sometimes back in SS Energy Letters, showing that if you take this MoS2 and tune the gap between the interlayer gap by inserting various things in between, in these few layer systems, you can make really advanced supercapacitors with fantastic properties. In order to understand what gives rise to these interesting properties in chemically exfoliated system, we looked at, and I'm showing you here, photoelectron spectroscopic data. So what we are doing is looking at the core level of molybdenum 3D5, molybdenum 3D3, this peak, and this bump here is coming from sulfur 2s signal. The circles are the experimental data, which can be fitted by assuming sulfur 2s, molybdenum 3D5, and molybdenum 3D3. It turns out that you can already see that the molybdenum 3D3 has two different peaks, one peak here and another shoulder here, which tells you that there are two different kinds of molybdenum in this system. And when it was fitted and the binding energies were compared, it turned out that this is the normal form. This very small amount that you're seeing, this bump here, comes from the so-called normal MoS2, which is the wide band gap MoS2 in the H crystallographic form. The entire talk today is then, what is this majority phase that I've created by chemical exfoliation that gives me such superlative properties in the chemically exfoliated sample, which has a very large binding energy shift. And I'll come back to that in a moment. But it was known from a very long time ago. See the publication date, 1973. There's a band structure work from Matthias, who showed that the normal bulk has a 2H phase. It has a wide band gap insulator from band structure calculation. But if you form a 1T phase, and I'll show you how these two phases are related in the next transparency very soon, and that forms a metallic MoS2. And this particular paper has influenced out the community so deeply that when you saw that we are forming a metastable state, we knew that Mr. Matthias had told us that the metastable state is the T phase, and the T phase is metallic. And how are these two related, the H phase and the T phase? It's actually fairly easy to visualize it, and let me help you along. This is the H phase, the stable phase. How do you visualize it? I told you that there's a layer of the metal, molybdenum in this case, that forms a hexagonal layer in the center. You have another hexagonal layer of the chalcogen, sulfides here on top, another layer below, and this top chalcogen layer and the bottom chalcogen layer eclipse each other. You can see that this sulfur is exactly on top of that sulfur, this sulfur is exactly on top of that sulfur, this sulfur is on top of that sulfur, forming a prism here. And the molybdenum is sitting at the center of the prism, so that if you look down from top, you will see this molybdenum, the hexagonal structure of the molybdenum around it, and you will see this sulfur forming the hexagonal structure, but you will not see this sulfur because this sulfur here will eclipse the sulfur that's below. Now think that I'm going to slide this top layer with respect to the bottom layer in such a way that the lower layer or the top layer of sulfur will come to the center of this hexagon. If you do that, then you form this structure. So just by dragging the top layer, bringing it to the center, now you can see that I can see the lower layer of sulfur, they're not eclipsed anymore. And you see that around the molybdenum, 3 sulfurs from the original layer on top, the 3 sulfurs below, forming a perfect octahedron as shown over here. So now by sliding the layer, I've created an octahedron of MoS6 unit from a MoS6 prismatic unit. I've already told you that this is the stable structure, and this is believed to be the metastable structure. This is prismatic, this is octahedral. And that immediately tells you that the crystal field splitting or the ligand field splitting, because the local coordination is very different, must change drastically. And in fact, it is very instructive to look at the crystal fields effect here. So if you take the crystal field effect of an MoS6 prismatic structure, then the molybdenum D level will split into a doubly degenerate level, a singly degenerate level that can take 2 electrons, and then there's a doubly degenerate level, another doubly degenerate level. MoS2 nominally molybdenum has 2 electrons because it's molybdenum 4+. Those 2 electrons will go here, and you can see this large ligand field splitting, and that's a fully filled shell, and that tells you why the H phase is a large band gap insulator. It's driven by this large ligand field effect driven gap between this dz square and the other orbitals that come next. The bandwidth associated with that is smaller than this gap, and that's why you have an insulator. What would happen if I rotate this triangle around or slide and bring the next triangle to form the octahedron? Now, when I form the octahedron here, we know that if it is a perfect octahedral field, then the crystal field would give me a splitting of a triply degenerate state below T2G levels and EG levels above. Remember, I have only 2 electrons of molybdenum, so they will occupy this triply degenerate state, and you can immediately see why this particular state will be metallic, because it's a partially occupied state. However small the bandwidth, maybe it doesn't matter, it will be conducting because it's a partially occupied band. And this is the reason why Matthias' band structure said that this is actually a metallic state. But also look at it and see that it's actually, its ground state is degenerate, which means it's Jahn-Teller unstable. The system would like to lower its energy by giving small local distortion of these sulfurs and molybdenums in such a way that it lifts this degeneracy driving gaps into the system. And in fact, it is known that it can give rise, if it is not distorted, the undistorted structure we call the T structure, but there are various possible distortions. And that distortion will give rise to a smaller gap. It will give rise to a singly degenerate level, which will accept these 2 electrons, and a small gap and a doubly degenerate level. So this triply degenerate level will then split into a singly degenerate level and a doubly degenerate level. And depending on how large this gap is, and the bandwidth of this, if the bandwidth is smaller than the gap, then the system will be a small gap insulator. And there are different kinds of distortions possible, and they're written as T prime, T double prime, T triple prime. What are these distortions that I'm talking about? Let me point out, starting with the undistorted T state, where you can see the molybdenum in the black, and you have these oxygen, the sulfurs, 3 sulfurs on top, 3 sulfurs below, forming the octahedron that I talked about. Think of now alternate molybdenum coming closer together such that the next ones become at a distance. So if I move this towards that, move this towards that, move this towards that, you can see that I'll have dimerization of some kind. And that dimerization, if I give rise to a dimerization of this kind, you can see immediately your unit cell from 1 by 1 will become a √3 by 1 or a 2 by 1 structure. And these 2 are equivalent description, and that is the T prime distortion that we talk about. It comes from, this is a short molybdenum-molybdenum bond, this is a longer molybdenum-molybdenum bond, and these dimers form a chain, and this long bond also forms a chain, alternating chains along this axis. Instead of dimerization, you can have tetramerization, where 4 molybdenums come closer together so that your unit cell is now 2 by 2. And that structure is known as T double prime. This structure is also known, it can form, though highly metastatic state. T triple prime structure is generated from a trimerization where 3 molybdenums come closer together. And you have a √3 by √3 structure that forms. The question then is, which one should form? Do I have the undistorted T structure, which is a metal, or one of these distorted T structures, primed structure, which will be a small band gap insulator? So there's a fundamental change in the transport property, which would mean their chemical property and all device properties would be completely different depending on which phase it forms. And one would expect that, well, following Matthias, we know that we can do ab initio calculation and figure out which has better stability. And when you do that calculation, of course, the H phase is the most stable, and that's my reference. And it turns out the T phase is highly unstable. The T double prime phase is slightly more stable, about 200 millielectron volt more stable than the T, and the T prime and T triple prime are almost degenerate. They're only 4 MeV apart. But it is saying that if a metastable state has to form, unless I kinetically stabilize the T state, thermodynamically it's likely to form T prime or T triple prime and not the T. It turns out that if you try to analyze the T phase, it is even kinetically not possible to stabilize because it is intrinsically unstable. It will spontaneously distort itself to go into one of the T double prime, T triple prime, or T prime phase simply because there are phonon instabilities associated with the undistorted structure. So it is unlikely to form T phase. Of course, in the infinite lattice, we do not know what happens when I stitch a small patch of this, one of this T inside an H phase, because that can stabilize it. So that question still remains whether such a patching in of a T phase is also possible. And the community, turns out, believed, as I told you, that it was undistorted metallic phase. Sometimes it said it's metallic, so it must be T. Sometimes it said it's T, so it must be metallic. Because we were very much influenced by this Matthias paper from 1973. And you can see there are a host of papers, even in the title, it appears as metallic 1T phase, conducting MoS2 sheet, etc., and many more. So the argument went either T phase is metallic, or sometimes they found some indication that it's a metallic state. And since all other phases would be small bandgap insulated, so they said if it is metallic, it has to be a T phase. And this is the time when we came into the field and asked the question, can we more directly determine what really the phase is and what its transport properties are, so that we know what device properties are being controlled by. So the question then breaks into which of these particular phases it's forming, which is whether it's metallic or insulated. And what I didn't tell you, the chemical exfoliation process, I'll not deal with that for too long. Most popular way of doing it is to take N-butyl lithium, intercalate it inside, and then exfoliate it by washing it off, because lithium gets in, separates out the MoS2 layers from each other, makes the van der Waals interaction even weaker, then it falls apart very easily. And then you wash it off to get rid of the lithium ions from the system, and what you have, few layer MoS2. And that's how you prepare the chemically exfoliated one. And then the question is, was the lithium ion necessary other than separating out the van der Waals layers so that I can chemically exfoliate the system? And I'll come back to this question at the later part of my talk. What I'm going to show you is something that was published some years ago, and it was driven mainly by this spectacular PhD student we had in the group, Banabir Pal, very ably supported by other members of the group. Banabir is right now doing his postdoc with Stuart Parkin in Halle. And we were very strongly supported by Professor Umesh Wagmare and his student for the theoretical input. And what I'm going to show you, some very fancy synchrotron photoemission work, which is done at Electra Synchrotron Center, and it is by these people that supported our experiment there. And so they're our collaboration partners in this work. Before I show you chemically exfoliated one, let me again retune your mind to anticipate what to see. What I'm showing you is mechanically exfoliated MoS2, and this is a work that we did long time back in collaboration with Professor Arindam Ghosh, my colleague from Department of Physics at IISc. And when you look at the core level spectroscopy, photoelectron spectroscopy, I had told you this bump is sulfur 2s. This is the molybdenum 3D 5-half, molybdenum 3D 3-half, and there's a bump coming from an impurity of slight oxidation giving rise to molybdenum oxide. We can fit the line shape very precisely. As you can see, experimental data are circled. This orange line is the theoretically fit. It turns out that even in the mechanically exfoliated one, we couldn't fit unless we brought in this small minority peak of another kind of molybdenum, which we would have called at that time the T phase. What I would like you to notice is that there's a large binding energy shift between the H phase and the T phase. The T phase binding energy is lower than that of the H phase. And this is going to play a crucial role in what I'm going to say after this. How do we do the photoemission experiment? A very quick one. Normally, here is the sample holder on which I've put a sample. Now, I've given two different colors to the sample, the gray sample and the green sample. because my sample may be inhomogeneous. You can think of it, there's an H phase and a T phase, and I'm interested in knowing the character of the T phase. Normally, the way we do the photo emission, we bring in photons. The photons fall all over the place depending on the spread of the beam, and that knocks out electrons. These electrons then go into my detector. I measure the energy of the detector. From there, I can plot the spectrum. If there's inhomogeneity, then I get signal coming from various places, and I get a very complex spectrum like this. If I'm interested only in this part, ideally what I would like to do is to, instead of doing it that way, I'll bring in the photons and put a lens in front of it and focus it down such that now I can get only the green spectrum. And then by shifting my sample and placing the gray in front of the photon or the gray spectrum, the sum of which actually is white that I saw in conventional photo emission. It sounds very easy, but to focus X-ray is very difficult, and to focus them down to a very narrow point is extremely difficult. And this beamline is one of the best in the world, where we can get the minimum photon size of 100 nanometers. So we are going to do photo emission with 100 nanometer, pixel by pixel, putting it at various points, trying to figure out what my chemically exfoliated sample looks like. When I look at the chemically exfoliated sample, you can see this is the sulfur 2s again. This is the molybdenum 3D 5-half, molybdenum 3D 3-half. What I can do is to integrate the complete intensity coming from here. That means I am trying to figure out where is molybdenum 3D on my sample substrate. Remember, it's not only few layer thick, these are also a few microns wide samples. So it's a very small sample. So I want to look at this sample and map it out. So I know my substrate does not have any molybdenum 3D. So I'm going to look at the molybdenum 3D signal that can come only from the sample. And I'm going to map that intensity. As soon as I do that, you can see that this is the substrate where molybdenum is not there. And this is one flake. This entire frame is about 13 micron by 13 micron. Each pixel is about 100 nanometer 0.1 micron. That's the resolution that we have. And I can map out the flake exactly. There's another smaller flake, another flake, another flake. That tells you how molybdenum 3D is distributed on my substrate. But that's not enough. I want to know where the H phase is and where the T phase is. Now, I've plotted the H phase spectrum because I can take a mechanically exfoliated sample, which is dominated by the H phase, and immediately I see that it's a very narrow signal compared to this broad signal. If I, in fact, compare the two and put the H signal with this one, you can see that in this broad signal, the higher binding energy side is contributed by H, the lower energy side is contributed by, as I know from my earlier experience, T phase. So now I'm going to take this energy window that I showed over here, divide it into two parts, the part that is mainly contributed by the H phase and the part that is mainly contributed by the T phase. One of the T phase, I don't know which T phase it is. And since I'm interested in maximizing the T phase, I can take this intensity divided by that intensity as a measure of the amount of T phase present on the face of this sample. So I'm going to map out this ratio pixel by pixel, and you can see that is shown over here. And that is what I'm seeing. And you can see that some places I have much more T phases. Some places in the molybdenum disulfide have very little T phase. Since I'm interested in the T phase, what I'm going to do is to focus down on that single pixel and do all my spectroscopy there after mapping out the entire frame. And I'm going to show you all the results from one single point after this. And that spectrum is what I was showing you. Now I can split it, decompose it into the contribution coming from this metastable T phase, and there's a stable H phase. This is very important. Now I know quantitatively at this spot how much is being contributed by the T phase, how much is contributed by the stable H phase. This I shall need in order to determine what phase I'm looking at and what property it has. So having known the abundance of the T phase relative to the H phase at this particular spot, then I turn to the question, how do I figure out this particular metastable state? Is it metallic or insulating? Now, this question is something that in photoelectron spectroscopy is ideally suited to answer. because we can look at the density of states or the spectral intensity at the Fermi energy. The fundamental distinction between a metal and an insulator or semiconductor is that a metal will have finite spectrum at the Fermi energy, at the chemical potential, whereas there will be a gap, which means for an insulator or a semiconductor, that means I'll say zero intensity at the Fermi energy. So all that I need to do is to go and look at the valence band where the Fermi energy is, and this is the spectrum from that particular spot on the sample of my chemically exfoliated sample. And this is the Fermi energy. The energy is referenced always to Fermi energy in photoemission spectroscopy. So I'm really interested in knowing that little part there. So what I'm going to do is, instead of showing you the whole thing, going to pull out a little part from here and look at it more closely. That little part I'm now going to pull out, and that's shown over here. And this red line is nothing but my chemically exfoliated, how the valence band looks in the vicinity of the Fermi energy. And I've also shown you the H phase, the gap system, to show you what is the reference of a gap, no intensity at the Fermi energy. And you can see that if I look at the Fermi energy, there is absolutely no intensity from my chemically exfoliated system. I don't have to know which T phase it is. The fact that this has no intensity at the Fermi energy tells me it's an insulator or a semiconductor. That tells me that it cannot be a T phase. It cannot be the undistorted T phase. It has to be one of the distorted T phases. It can be T prime, T double prime, T triple prime. So the question is which one it is and how do I figure that out? In order to figure that out, we looked at it in more detail and asked, okay, the whole valence band spectrum must be characteristic of which phase I'm looking at. And since I know the T prime, T double prime, and T triple prime phases, and I can structurally optimize it, I can do a density functional theory and predict what the valence band should look like. And then compare it the valence band that I've collected from experiment, and therefore know which phase I'm looking at. But before I do that, I have to make sure the theory I do is actually competent enough to tell me the valence band spectrum. And so I take a known system, molybdenum disulfide, in the H phase. And in order to do that, so first I show you what is the H phase valence band that looks like. It looks exactly like this. This is the experimental data. And then I do various levels of approximation, making it more and more complex, more demanding calculation to get the best description of this experimental data. I'll not go into the detail of that. Eventually, it is the GW calculation that gives us the best data, and I'm showing you the result. So the calculated result is shown over here. And you can see that the agreement between the experiment and theory is satisfactory enough for me to say, okay, fine. I'll now extract the metastable state valence band structure from here and compare it with the calculated, GW calculated valence band spectrum, theoretically estimated, and that will tell me which is the phase that I have got. In order to extract from this the valence band spectrum, mind you, there's a problem. The problem is that this is not a pure T or metastable states contribution. This has contribution from some H phase. Remember the core level we looked at, so I know exactly how much quantitatively H level contributes to this particular phase, this particular spectrum, and I can subtract that out. And that quantitatively, I know exactly this much of H phase is contributing to this total spectrum. But also there is the additional problem, because I'm looking at a very thin layer of molybdenum disulfide, and it would contribute the substrate. And the substrate also has a valence band, though not as structured as this, but I need to subtract that out. And that also can be subtracted out by looking at the core level of the substrate seen through the molybdenum sulfide, and that is contribution comes like this. So I'll subtract this and this out from that one. What remains is the valence band from the metastable state. When I do that, this is the metastable state valence band spectrum. And then that is the one that I compare with the calculation. I'm showing you the final result. We compared with T prime, T double prime, T triple prime. Turns out it is the T prime state that gives the calculated spectrum that matches very well with this valence band spectrum experimentally obtained. telling us that it is the T prime phase, which is not unreasonable because among all the distorted states or this metastable state, T prime and T triple prime are the lowest energy states and T double prime is not. So it's not totally surprising that we are getting to the T prime state. So what it forms, the chemically exfoliated state, is not the T state and not a conducting metallic state, but a small band gap of about 90 millielectron volt semiconductor. This is the conclusion we came to. But this is a very unconventional way of doing things. Normally, as I said, that we know the geometric structure and we can calculate the electronic structure. Here, we experimentally determine the electronic structure and concluding about the geometric structure. Is there a way of doing it more directly? It turns out the results were there for the last decade and in the literature, and it was staring at our face, but we didn't look at it carefully enough. Let me explain to you what I have in mind. Raman signal, which is often used for 2D materials, for graphene and what have you. If you look at before chemical exfoliation with mechanical exfoliation, let's say, or bulk system, what you see is two beautiful lines which are due to A1G and E1G. We are doing micro Raman on various spots, so that's why different spots, but that is not relevant in this particular context. So we get this and no other signal. But the chemically exfoliated one shows me this remnant of the H phase, these two, the A1G and E1T2G, but shows me many other strong lines which are often comes as J1, J2, J3, etc. These are the signature of the metastable state because that doesn't exist here at all. And they're very strong. And therefore, I should be able to use them to determine what the structure is because the frequencies must be extremely sensitive to the structure. And these frequencies, these kind of Raman spectra have been reported in the literature for the last 1 decade. In fact, we just collected all the data and plotted them. What I'm showing you, Raman peak positions collected from various papers, and this compilation is published here in this paper, in different years. And you can see that there's very strong consistency. The peaks are all vertically aligned. That means it didn't matter who did the experiment, how they did the chemical exfoliation, they always got the peak positions in Raman more or less at the same energies, same frequencies. But I've used two different colors, red and blue. That is to indicate that what did the authors attribute the phase, metastable phase to be. Red implies they attributed it to T, the symmetric metallic state, and these are the distorted phases. The first statement of distorted phases is true on a T prime. Everybody claimed it to be the T phase metallic state. This is our paper, 2017 beginning, where we showed also from photoelectron spectroscopy that it is actually a metastable T prime phase. And then on, there's more and more frequently people calling it T prime phase. But how do I know? Because these frequencies can be calculated. And calculated frequencies existed in the literature. We just collected from different theories the range of frequencies reported. And if you collect the H phase and plot it here, then this is a range of reported H phase. So those are the H phase signals. The remaining ones are coming from the metastable phase, and the metastable phase, the T prime phases, the calculated values are shown over here. And you can see that they account for all the Raman frequencies that have been reported, showing that Raman data, if it was correctly interpreted, we should have concluded that it is the T prime phase that forms. Having established that it is the T prime phase, let me go on to ask the question that why did people believe it to be metallic? Because T prime phase, I'm insisting, is a small band gap insulator. Now that's really a challenging question because people found them to be metallic, and that's why I call them metallic. This is where we started asking the question of what is the role of lithium ions? What are they doing there? In order to understand that, and this paper is published in this particular reference, and you can look it up, and this again, Debo Schmitter's thesis work, the previous one also. This is very recent. She is a PhD student at the moment, supported by other members, as well as the electron spectroscopy group of Electra. So what Debo Schmitter decided is that since the previous work that we reported earlier, we didn't find any lithium because we had washed the sample thoroughly to get rid of lithium. Lithium level was below the detection level. Devoshmita decided that she will not wash it. She will look at it with the lithium and try to see what is happening. This is the H phase that is the stable phase. And then the chemically exfoliated sample without any wash, zero wash, you'll see this notation, has this very intense signal coming from the metastable state. And then she compared with the very same sample after washing, 12 wash, it has, but every signal of the metastable state is going down in intensity. That tells you that lithium ions actually are helping the system kinetically get into this metastable state and preferring the T prime state that you have configured. So lithium ions play a very important role in stabilizing the metastable state. But electronically, what is it doing? Because when lithium ions are there, they will donate electron to the system. They'll dope the system. And let me tell you that story now. This is the molybdenum 3D signal, zero wash. And since you already know what we're doing, again, we are going to do this highly focused photon beam, and we'll look at, if I take the whole molybdenum 3D, I can show you what the flake looks like, a beautiful molybdenum disulfide flake. We know that this part, higher energy part, comes from the H phase, lower energy part comes from the T phase. T prime phase, I'm going to take the ratio and I'm mapping the ratio for you. When I do the ratio mapping, you see that zero wash sample is fantastically populated with T prime phase all over, not like what I showed you before, which was some places a little bit. There we choose the one that has the highest T prime phase, but it's almost uniformly T prime phase everywhere, with some H phase, and I analyze the data, I find it's 80% T phase and 20% H phase. Another thing that we found that in this particular case, because I have so much of T prime phase, that in order to fit this data, I needed this bump, which I didn't need before. This bump actually comes from a plasmonic satellite, indicating some kind of a free electron response in the system. And that's when it is showing up. Keep this in mind, it will become important in a moment. And then she took the 12 washed sample, which is thoroughly washed, where you don't detect any more lithium, and did exactly the same thing. This is the flake and this is the ratio. You can now see that the T prime phase has become much weaker all over the phase, simply because I have removed lithium. Lithium went away with its electron and T prime phase got converted hugely back into the stable H phase. But we find the place where it has the maximum T prime phase and we extract we find it's about 70% T prime phase and 30% H phase. But watch here, I do not have those those bumps, as if that the plasmons are also weak in this system when I pulled out the lithium and it went away with its electron. These electrons were responding as free electron in the system somehow. And that was stabilizing the T prime phase. Then let us compare the zero wash and the 12 wash sample. There's too many things. What I'm going to do is to pull out these two molybdenum spectrum, the fitted data of the zero wash and the 12 wash, and compare them together so that I can see what is any subtle difference there. And that is what is being done here. The solid lines are from the zero wash sample. The lower binding energy, I've normalized to the same intensity because I want you to focus on the energetics now. And energetically, you can see that this is the zero wash H sample. This is the 12 wash H sample. They are shifted a little. Of course, the H and T are shifted a lot, that we already know. But there's a gentle shift in the H phase, whether it is in the T prime phase or in the H phase. Likewise, the T prime phase signal binding energy also is slightly lower binding energy if it is zero wash, but when I wash it thoroughly, it shifts a little higher. And that shift is approximate. Not only shift, you can see that the plasmon is intense in the zero wash sample, but it is not there in this other thoroughly washed sample. And this shift is in the order of 0.3 electron volt. The same thing I can do with sulfur 2p. I'll not bore you with the detail, and I show you directly the result. It turns out that also here, I see the sulfur levels also, the H phase signal and the T phase signal both for the unwashed sample is at lower binding energy of high binding energy of 0.3 electron volt, whereas the thoroughly washed one is 0.3 electron volt lower binding energy. In fact, it turns out even the valence band, and this is the valence band spectrum of the 0 wash sample, which is the black dots, and the 12 wash sample, which is the red one. You can see the 12 wash is actually shifted this way. We're interested in knowing the shift here, and that is the expanded form I've shown here. That shows about a 0.2, 0.3 electron volt shift in the leading edge. This is the H phase, which has a wide band gap. So every time we wash the sample, it shifts. Why does it happen? Now, let us see what lithium can do. Imagine that I have very low amount of lithium. My Fermi energy is here. I put lithium into the system. Lithium dopes electrons. Where will those electrons go? The electrons will go here. That means my Fermi energy will move up. So between the lithiated sample with Fermi energy here and the unlithiated sample or well-washed sample, the Fermi energy here, I should see a difference. But I don't see the Fermi energy difference because photoemission always aligns the Fermi energy. Before seeing recording, I align the Fermi energy. So that what happens now, you see that the core level will show a shift, the valence band will show a shift, and that shift is actually the shift of the chemical potential or the Fermi energy because it got doped by lithium. This lithium doping shifts the Fermi energy up, showing all occupied levels showing the same amount of shift, and so this doping makes the system appear metallic. So small band gap doped with lithium, doped with defects. It turns out sulfur defects also will dope the system with electrons. And there's a good reason to anticipate from theoretical consideration that when you dope the system with electron, it will favor the T prime phase because it has a small gap compared to the H phase. So there's an energetic reason. Having understood this part, that chemical exfoliation leads to the T prime phase and not T phase. Lithium ions are present in various quantity and they dope electrons in the system. There are sulfur vacancies also known. They also dope electrons in the system. And these doped electrons stabilize the metastable state. And these metastable state stabilized by electron doping, those electrons, doped electrons, make the T prime phase appear conductive. So it's a doped system, and that's why it's conductive. Now I'll quickly turn to a heterostructure and show you how beautifully heterostructure of MoS2 can be addressed. Though it's not chemical exfoliation, the reason I'm bringing it in is because it was believed in this heterostructure, mechanical strain makes the MoS2 go over to this metastable state. And we wanted to see it by the same technique. There's unpublished results, and this is a collaboration with Professor Arindam Ghosh, Professor Manish Jain, and their PhD student, Meg of ISC, Physics Department, and our partners, Luca Gregorati, Matteo, and Hickman from Electra. Again, driven by Devoshmita. So the device structure that I'm telling you about looks like this. You have a silicon dioxide substrate on which I'm going to build up my sample. I put an HBN, which makes it absolutely neutral so that it doesn't couple to the otherwise substrate here. I lay down the molybdenum disulfide on top. And then I put a graphene on top, and this graphene is supposed to put a compressive stress on the system. And some part of MoS2 is not covered by graphene, some part is. Some part of graphene doesn't have MoS2. Beautiful, but actual device doesn't look like that. There are all these multiple papers that talk about this compressive strain and the possibility of compressive strain driving a metastable state, because people see that the metallicity or conductivity goes up in this particular configuration. This is the idealized structure. Looks very beautiful, but the real life picture, if you take an SCM, looks like this. And it's not going to tell you much. These legs that you see are all the leads of the device to measure its properties, transport properties. and you hardly see anything. And these are the wishful thinking of through ACM that I can place. But what I want to point out here, the power of the technique that I talked about, because now I can say, okay, show me the molybdenum 3D intensity. So I'm going to map out the molybdenum 3D intensity pixel by pixel. When I do that, this is what I see. Now, there is a surprise because this is, I told you, the legs of the conductivity probe. There's no molybdenum in it. It is coming because of inelastic scattering. It gives not a peak of molybdenum 3D, but a flat background. And there's a very easy way of getting rid of this flat background. So you monitor in the flat part and at the molybdenum 3D peak, and you subtract out this inelastic scattering. When you correct the inelastic scattering, and you see only the molybdenum 3D, and you see in your device the molybdenum 3D beautifully showing up, this black part are these leads that you have seen. So this lead is shadowing this one. This lead is coming from here. And then you can see a little bit of a shadowed part here. That's where the graphene is. There's molybdenum more intensity here. Graphene is here above molybdenum. So molybdenum looks a little less intense. This is a chemically exfoliated molybdenum disulfide. Mechanically exfoliated molybdenum disulfide. So now I can put my pixel where I want. If I want to study under the graphene, I can put my pixel on A, C, and B. Those are these spots on this device, and look at what molybdenum looks like. If I want to see what graphene doesn't do to it, I can put it here and here, E and F. I can choose, and I can see what molybdenum 3D signal I get. And I can put on graphene to get reference graphene without molybdenum mucking it up, signal from here. So I'm going to collect signal from each of these points and show you what conclusion we come to. I can also look at the boron, just to show you the power of the technique and get rid of the inelastic scattering. You can see the boron nitride is shadowed not only by the electrical leads here and here, but also by the molybdenum 3D flake, which is here. So you can map out everything. That's another device structure. I'm not going to talk about that. This is the molybdenum, the Raman spectrum, because that can sensitively measure the strain. What we're looking at is that molybdenum disulfide on HBN and one that is covered by graphene where the strain is supposed to develop. And since I'm interested in this part, if I pull it out, I see that there is indeed a shift in the phonon frequency of 2.1 centimeter inverse, and that translates into a composite strain of 1.2%. Knowing that my system is strained, we now look at the electronic properties by looking at the photoelectron spectroscopy. When I do that for both the devices, what I find, this A, C, and B are all under the graphene. You see A, C, and B are the solid lines. All the signals are together of molybdenum 3D. And whenever I'm looking at E and F, which is not under graphene, which are those dots, they are shifted. The same molybdenum disulfide. For both the devices that happens. B, which is under the graphene, is shifted to the left, and A and C, which are not under the graphene, are shifted to the right. So there's a consistent shift of the molybdenum 3D. But the line shift tells me that this is absolutely the H phase. If I shift it, it will exactly superimpose on that. So it's not that I'm getting two phases, which will then show me a broadening, which I'll be able to fit by two components. I cannot fit two components. It is the H phase, but H phase is shifted. And then I go and look at the sulfur 2p. Again, I find the same kind of shift. Whenever under the graphene, lower binding energy, whichever is the device, whether sulfur signal or molybdenum signal, by about 0.4 plus minus 0.1 electron volt. The same happens with the valence band, and I'll not spend more time on it and tell you what really is happening. That means here also I have a problem of referencing, though the H phase is getting shifted whenever it's under the graphene. What happens is that this is MoS2, H phase is a wide bandgap insulator. And it has defects distributed. It is a defect that pins the chemical potential or the Fermi energy if you don't have the graphene on top. And that chemical potential actually is close to the valence band top, because it is known that the defect level just lies just above the valence band. But when you put the graphene on top, the referencing is the graphene chemical potential, which lies further above. And the alignment of the chemical potential shifts all the spectrum that are under it further away. But that is the phase that becomes more conducting. Now your reference to the graphene chemical potential, and that is the one that gives rise to the shift, and not strain driving the formation of a metastable state. So the conclusion of this part is that though it was believed that the compressive strain, which does exist due to the graphene overlay, does not drive a large-scale transformation of the H phase into any kind of metastable state, but the chemical potential gets referenced when it doesn't have graphene to a defect state, but in presence of graphene to the graphene chemical potential, and therefore the transport properties change drastically. This is something that I'll not talk about. If you're interested, basically there's some issue, very interesting but complex issue of how do you build this T structure or T prime structure inside the H phase, because I showed you that everywhere this metastable state forms, but doesn't give me a complete transformation. So there is a transformation, and this can transform back and forth between H and T phase, depending on whether I take out the lithium ion and push it back, or I heat up the sample, then it goes back altogether to the H phase. This transformation, that means it is an integral part of the lattice. How you stitch the metastable state in the H phase is a question that you had asked, and that paper in detail you can find. There's a lot of very interesting details that arise from that is discussed here. But let me end, because my time is over, thanking you for your patience. Thank you very much. And I'll stop sharing so that I can get back to the mainframe. Thank you.
Thank you so much. Let me, oh, it looks like our hosts have put up the slides. That's perfect. So the first question I have is, how important is the uniformity of doping? You showed how that the shifts are just critical to the electronic properties, but can one measure then the distribution of dopants and see heterogeneity of, say, transport or electronic structure?
Very good question. Very good question. And there is heterogeneity. So basically what is happening, lithium dopes, but it sort of forms a locally doped system. It doesn't allow, the doping level is not enough for it to be a totally metallic system of free electrons that are running around. How do I know this? I know this when I extract the spectrum corresponding to the metastable phase. It always has a width that is much larger than the H homogeneous phase, which tells me that there's local heterogeneity. There are local chemical potentials at different spots, even within the 100 nanometer scale that I'm looking at. So I need to have a much finer probe to be able to separate them out. So for me, it appears as a broadening, which is a heterogeneous broadening in homogeneous broadening.
And has anyone been able to map those dopants and then the varying electronic structure that?
I do not know of it, but STM would be an obvious tool to do, right?
We can talk in half an hour. The next question comes from Baidu, and the question is, the research on MoS2 has been very active over the last several years. Can you give your perspective on what's at and just beyond the horizon in terms of where that research is going now?
Oh, that's a tall order. I mean, basically, I think nanoscience, is such a mature field that it is now almost a tool. So almost everything can be made into nano, and there's a whole slew of toolkit to do so, different ones, depending on which one you want to do. And so tune the properties, and people are doing that. For any system that you talk about today, there's a whole lot of activities in the counterpart in the nano field. So I think anything that seems interesting, for example, I mean, we have seen this tremendous excitement about the hybrid perovskite, halide perovskites in recent times, which was originally driven entirely from the photovoltaic and the bulk material, thin film material, but a completely parallel stream of the nanomaterials of these have emerged, which are equally exciting and giving rise to many promises.
Mm-hmm. Terrific. And now what I'd like to do, I think what I'll do is take over the screen here, if I'm allowed, and I'll introduce our panelists. Let me, here. Yeah, that should be working. Okay, so our first panelist is Dr. Roy Velasamy, who's a professor of intelligent systems at the James Watt School of Engineering at the University of Glasgow. Prior to his time at Glasgow, he held faculty positions at City U Hong Kong and the University of Hong Kong. His multidisciplinary research blends device physics with materials chemistry and electronic engineering, focusing on intelligent devices and sensors, wearable thermoelectrics, piezoelectric sensors, and neuromorphic devices. He received a gold medal for his sensor platform at the International Exhibition of Inventions in Geneva and was a Trill Research Fellow at ITEP, along with having received many other awards. Our next panelist, Dr. Zhou Li, is an associate professor in the Department of Materials Science at Fudan University. Her research interests include functional polymer composites for electronic packaging and stretchable electronics. She was a recipient of the Shanghai Pujang Program, recruitment program for young professionals, and Shanghai Rising Star Program. And she also won the IEEE EPS Outstanding Young Engineer Award. She's the president of the Shanghai chapter of the IEEE EPS and vice president of the IEEE WIE Shanghai Affinity Group. And our challenger today, no, it's not advancing. Oh, am I still here? I'm afraid people might have frozen. Are we able to hear me?
Yes. Yes.
Okay.
But
you're not advancing, so maybe Alice, you can have your people show the PowerPoint.
Okay. Yes. No problem.
And if I disappear, please take over the panel for me. But I'll introduce our challenger. Govindan Kuti is a PhD student in Professor Zhang Liu's lab in the Department of Materials Science and Engineering at NTU Singapore. He's already submitted his thesis and he's moving to research, congratulations on that, and is moving to research fellow position at the Center for Advanced 2D Materials with Professor Antonio Castro Neto in the Department of Materials Science at National University of Singapore. He received an Indian Academy of Science Fellowship and NTU Research Fellowship for his doctoral studies in Singapore. And so if we can, let's put the panel up. I no longer seem to have a cursor here, which is disturbing. And I'll ask Govindan to give the first couple of questions here for our speaker.
Sure. Thank you, Prof. Vies and Prof. T.D. Sharma. It was a wonderful talk, very informative, very advanced as well. And I thoroughly enjoyed listening to the talk throughout. And coming to the lecture, some of the points that I want to ask you is that as you mentioned in your talk, that lithium doping is actually inducing the metallic nature in the 1T prime phase of MoS2, right? So basically, there were like previous studies also on the MoS2 in the 1T phase of MoS2, like the potassium doping, the K doping, which also is in metallic phase. So do you think it is a universal nature of this dopants like lithium, like the metallic doping, like the lithium or potassium, like induces the metallic nature? Particularly in this case of chemical exfoliation, right? The lithium dopant induces the metallicity, but in the other CVD techniques, they have also, I'm sorry, I cannot see the screen now.
Okay, I can hear your question.
Okay.
Please.
Okay, so in other synthesis process also, like through CVD and CVT, like the chemical vapor deposition and the chemical vapor transport, there also people have directly grown the onti phase or onti prime phase, and they are also metallic without the need of having a dopant. So what do you think is the major factor playing here?
First of all, let me quickly touch on several subtle points. First of all, if you dope the system, you take your, let's say, mechanically exfoliated MoS2 and you dope it with lithium, potassium, etc. If you're able to dope it, then it will show conductivity, simply because you're doping, if sufficiently. But life is never ideal. What happens is that MoS2 always has defects, sulfur vacancies.
Yes.
The sulfur vacancies also dopes electrons. So when you have MoCVD and other methods, in fact, very well known that if you do a plasma etching of MoS2, you can make it conducting. That those are all coming because of sulfur vacancy. I suspect sulfur vacancies, every sulfur vacancy dopes 2 electrons, not 1. So it's a very strong doping. And also the peculiarity that I said, that once you dope and you have a sulfur vacancy, actually the vacancy level drops down and you dope into that level. So what would happen is that your conductivity would go up. I would like to give one small clarification. When you talk about metallic, you have to know that every semiconductor or insulator at a finite temperature is always conducting, because there's some electron hole excitation. The question is, when the band gap is small, when the temperature is high, and when you have doping, these are the 3 things that favor getting conductivity. And I suspect that even in absence of lithium, you can get conductivity because of sulfur vacancies. And this, I'm sure, has been talked about in the literature.
Yes. Thank you, Prof. Sharma. And another thing I want to ask you is that how does we control the concentration of lithium doping and in the process, and how does it affect the nature of the material?
Ideally, I mean, it is not, we are not able to do that experiment. Ideally, what I would like to do is to actually take a mechanically exfoliated MoS2 and try to dope it by evaporation in UHV of lithium, and that kind of experiment can be done. I don't even know what would be the consequence of that doping, whether that doping would give rise to, would have enough energy to convert locally the H phase of MoS2 into a metastable state. I do not know. I definitely know in the chemically exfoliated state it happens, but then the pathway is very different, right?
Yeah.
We tried to control the lithium doping by successive washing stages, but it turns out one wash and lithium vanishes because we wash it with water. With one wash, we find that we do not find any more lithium within detectable limit of our photoelectron spectroscopy. There may be some still remaining, but below the level of detection. So we tried, but we couldn't control the level of doping by that method.
Okay. Thank you, Dr. Sharma. And another question I want to ask you is that through the process of chemical exfoliation, right, people are always like, our material scientist people, like in our community, we are very much interested in like single layer of MoS2. Like more studies have been done on single layer. So through this chemical exfoliation process, how do we control the different layer thickness as a whole?
Yeah, you're absolutely right. As of now, we have a distribution of different layers, thicknesses, and it's not possible to get only one kind of layer thickness from chemical exfoliation. That is not possible. So get a distribution of layer thicknesses.
So the same claim for this, the doping studies and the shifting of energy levels, right? So this
for the heterostructure, not the heterostructure part that I talked about was mechanically exfoliated single layer of MoS2. Okay, so that's why I brought that in, because there is a belief that the mechanical strain coming from graphene converts it into the metastable state. But what we show that it does not convert to the metastable state. It remains in the H state, but there's a change in the local chemical potential under the graphene. Okay. And that's why the transport properties change. And so the device property would be affected.
So what was trying to ask you is that, so the same observation that you have seen in few layer flakes, right? So does it apply to like some layers, single layers, bilayer or trilayer, or it applies to a whole lot of thickness for the number of layers?
This is a wishful thinking statement on my part, because we don't have experiment to support that. And we believe that it is valid for that. The reason, to the extent we can say, we looked at many, many flakes with different layer thicknesses. And we can get a feel for the layer thickness by looking at the substrate to molybdenum intensity ratio in the same technique. And we see that there's no difference between different flakes. The essential conclusions that I have given today are robust with respect to the layer thickness. We have not looked at any with a single layer, but that's a different question.
Thank you, Dr. Sharma. And one final question I want to ask you is that, so we are like synthesizing like the yield. I want to talk about the yield of these flakes that we produce through this exfoliation techniques, right? And how does like it catch up with the commercial ones that we use for the aforementioned applications, such as like supercapacitor or HER, right? So that were mentioned in the talk. So how does it like catch up?
Those are also at the moment on laboratory processes. What I showed you is the same methodology I used for doing a supercapacitor as well as for making these flakes, with some additional precautions in each case, because the end results were different. Because we had to avoid oxygen exposure, etc., more critically when I want to do electron spectroscopy, because it's very surface sensitive, right? So that kind of care. But otherwise, it was basically the same process. So the yields are the same. It's not a different process of chemical exfoliation that we used.
Okay. Thank you, Dr. Sharma.
Copious amount of exfoliated.
Okay. Thank you, Dr. Sharma. That's all from my side. Thank you. Thank you.
It's been my pleasure.
And let's turn to Professor Lee.
Hi, Dr. Didi. I think it's a very impressive talk. And actually, before the talk, I was going to ask you about the education of the graduate student and how to motivate the people and graduate student and postdocs in your group. But after listening to your talk, I think it's so impressive and interesting. So I would ask some technical questions first regarding your talk.
Thank you for the kind comment. I hope my students are listening.
Okay.
If they're not, that this is being recorded, so you can play it for them.
I'm not repeating it. I'll make it mandatory. Start the day with a repeat of this sentence.
So we'll time mark that quote.
Okay. All right. So technical questions first. So I think the doping story of lithium ions during the chemical exfoliation is interesting. And I'm just curious, is it similar to the semiconductor doping that when you increase the concentration of lithium ion that you can tune the conductivity? And also, if you can tune the conductivity, will that be beneficial for the applications such as supercapacitors?
Yeah, absolutely true. In fact, in the case of the supercapacitor, we intercalated it with sodium ions. That particular paper that I talked about in ACS Energy Letters, that was with sodium ions. And in fact, the different extent of doping, of course, makes a tremendous difference in the transport properties. And you can get to higher and higher conductivity and higher, you can tune the properties very, very significantly depending on the doping level. Now, as for the experiments that I presented, of course, as I said, that we had difficulty by that method of controlling the doping. But in a device, I can do that much more easily.
Okay. And also, that partly answer my second question, that since you are using lithium ion kind of salts to exfoliate MoS2. So what will happen if we change it to other salts or even some organic molecules that is insulating? So if we are using an insulating material to exfoliate it, will we see similar result with the mechanically exfoliated MoS2?
Very interesting question. I don't have the answer. I'm going to rush after the talk to look up the literature. I'm sure there's enough literature, because though this is the most favored route to making a chemical exfoliation using N-butyl lithium, but I think there are other methodologies, including trying to push in water, etc. And one should see whether in such cases we get different extent of metastable state. So, and that can be controlled to some extent by looking at the Raman spectroscopy, which is an easy tool and gives you a rough idea by looking at the intensity of these metastable states. So one can get some feel for it. I don't have an answer, but I think the answer is out there. And it's thank you for the beautiful question.
Okay, thank you. And also, I think for MoS2, we see the band structure and structure change after we have the exfoliation, doping, or mechanical stress by putting on different things. So do you expect that other 2D materials have similar behavior like MoS2 when they get so thin?
Absolutely. I mean, strain certainly would affect the electronic structure strongly. I mean, depending on how much strain you can give. And if you are able to dope or if you are creating defects, they all will affect the properties very, very drastically, other 2D materials as well. There's absolutely no question. Now, the question is that and I again don't have an answer, but I would immediately think, see, MoS2, when I'm making intrinsically naturally, it has a certain amount of sulfur vacancy. Now, what is the synergistic effect that I get? Having those sulfur vacancies doping 2 electrons each sulfur vacancy, there's a range of sulfur vacancies that always is there. And then I'm putting lithium or strain. So I already have some defect levels that are populated. So it's not only a question of the intrinsic ideal materials band structure getting strained or doped. You also have a defect level that is already populated. And how that responds. So these are the subtle questions that one has to ask, and it will be system specific, how much the response would be. But certainly, these effects exist in other materials as well.
Yeah, that answers my question. So I think after talking about those technical issues, the second thing I'm curious about is motivation of the young scientists or scientists to be in the lab. So as a senior professor in India, so usually what will be your suggestion for like young faculties like us to motivate the graduate students and postdocs in the lab?
Well, I think one thing is, of course, I mean, I don't have to tell you, Professor Lee and others here, that you people are anywhere leading from the front. They take you as an example and they follow that example whether they're aware of it or not. That's the first and the foremost thing. They see you and they may complain among themselves saying that, ooh, that person, she works just too much, driving us crazy. But it would be there. I mean, this is I'm very fond of pointing out to my students that the way I get my students to unify is by providing them with a common enemy, myself. And they can exchange their notes of how terrible I am and bond together. So but as I said, it is really that you as an example. And the other thing that, again, I don't have to tell you and you know, of course, is the fact that I try to tell my students that there is no problem that is good or bad. It is you who make a problem good or bad. Mm-hmm. It depends on how deeply you look at it. And very often it happens. It is the students, and now I'm talking to all the students who are listening, they make the problem a good problem or a bad problem. It is the intensity with which they are trying to understand. That makes the difference. It is the initiative that they take. It is that step that they take, which the supervisor did not say. That makes the difference. And then the supervisor comes along to package it nicely and to present it to you. Mm-hmm. But it is them, and that's, I would like to acknowledge. All my students throughout my life, they are the ones who teach me, and I don't teach them.
Yeah, I find many leading scientists say the same thing.
Because it's true.
Mm-hmm. All right, thank you.
Nice.
I think that's all my questions.
Thank you very much for the wonderful set of questions. Thank you.
Thank you.
And Professor Velasamy, it's your turn. You've been very patient.
No, so thanks very much, Professor Sarma, for a wonderful talk, and thanks, Paul, for a introduction, wonderful introduction. Thanks for everyone's time. So I have very straightforward question. When you with a couple of technical questions. So a lot of people working on doping on those two-dimensional layers, two-dimensional structures, and so on. But so there are ways to physically vapor deposition. All right, so you can do with lithium or any ion. But however, as a chemist, you can explain us, is there any way to more selectively doping? Okay, selective doping. For example, one of the, I'm looking at the application because I'm working at the School of Engineering. So look at more on real-time applications, real-life applications. So metamaterial, I think you should be heard of this for wide variety of things we can do that. So I was thinking, like, if you use two-dimensional structural molybdenum sulfide or any other, including graphene, if you have a very selective doping chemically, but that particular area with certain ions and so on, then you can completely change the optical properties in a, you can't in a brilliant manner that's really have multiple from high frequency, like 4 terahertz and all different kind of domain. So that's, I would like to hear from you as a, you're a chemist, because physical vapor deposition maybe, it's, as you said, it's always end up in a heterogeneous, it's not homogeneous anyway. So.
See, very tough question, and I have no clear answer, and I'm just trying to do loud thinking, really, ab initio right now. In order to do the chemical method of doping, what are the toolbox that I have, to approaches that I can have to chemically dope certain sites? I can come in with a ligand with a certain reactivity, but then it sees that the sulfur layer on top, it looks pretty much the same everywhere. I cannot say that go and sit there. One possibility would be, see, selectively doping in a structure. One thing that one can try to play around with is that whether I have the dopant interaction, if I can make it stronger than the dopant, well, not very much stronger, comparable to the dopant substrate interaction, then there will be a tendency for the dopants to come together and not dope, but at the same time try to come together so that you can have a structure. And then the perimeter of that, I mean, if you want to give, because you talked about metamaterial, where the geometry plays a very important role.
Exactly.
Depending on that's going to be a very tough question, because now you have a free boundary. That free boundary is going to lower its energy, and that's what is going to drive how it's going to be. Yeah. So unless you do some kind of patterning, which is not a chemical method, which has to be a physical method. By doing patterning, you can come combine a physical and a chemical method, give it a patterning such that there's an identifiable change in the structure, and then target this difference on the surface there, which is given by the patterning, to give it the structure that you want. That's a very broad statement. It's not specific, but I would start to think of it in that way.
So it's just, I'm just brainstorming, actually, this year.
Yeah,
of course,
exactly.
no,
And all that I'm doing is also just talking.
Trying to
lot of thinking.
yes.
So everybody is welcome to join in. I mean,
yeah, geometry, yes, that for sure we need to have a real like lithography or any imprinting. We got to do that at the end. So get right geometry, and then you go for a chemical kind of doping methods. Yeah, I agree. Yeah. So what I wonder is, when you talk about transport properties, so we are talking about you have lithium doping, it's ionic transport, and molybdenum sulfide itself as semiconductor, where you can have electronic or whole transport. So at the end, you have a kind of a mixture of both ionic and electronic transport. That how we are going to say that for particular use. If you use capacitor or anything is fine because those are all work on ionic conduction. But I'm going to use for a transistor because one of your structure is looking like a MOSFET structure. You have a silicon dioxide, hexagonal boron nitride, and semiconductor at the top. You have a graphene. It's a conductor basically. So you have a beautiful MOSFET structure. In that case, it's really if you have ionic transport, you will not get any workable device with the right switch on values and so on. So how we are going to solve this issue?
Let me just, maybe I gave some misled you into thinking that there's ionic conductivity. There's no, except for when we are talking about supercapacitor, etc., leave that out aside. For all the other devices and the chemically exfoliated one, there's no ionic conductivity. And the ion doping level is very small, and we're not talking about ionic conductivity. What we are talking about is that every lithium ion donates an electron into the system, and the conductivity enhancement due to those doped electrons.
Okay.
That is what. Okay. And in fact, also one rather speculative statement that I made was that when you dope, you tilt the energy balance from H towards T prime, not necessarily all the way, simply because H has a very large band gap. And if you want to dope electrons so high up, it's not energetically stable. But if you locally can give some distortions which make it look like one of these T prime phases, that has a much smaller band gap. And then doping becomes much easier. And that, I suspect, is the reason why we showed that lithium ions actually play an important role in kinetically giving rise to more amount of this metastable T prime phase.
It looks somewhat like a pinning, some kind of pinning.
Exactly, it is pinning. That's why I also kept referring to the defects. If you didn't have the lithium ions, then you have a certain pinning in the defect level. Okay, and then if you bring in the lithium ions and that dopes electrons, it doesn't become conducting, but it moves the chemical potential up, bring it closer to the conduction band, bottom of the conduction band, and we know exactly how much it's shifting by. That is the shift that we saw in our measurement. We know how much the chemical potential is moving up by. So how much the band gap is effectively decreasing, which at room temperature then gives rise to higher conductivity.
Great. Okay. So last in your talk, you talk about a kind of device. Yes. So as I said, it looks like a MOSFET structure. Do you have anything? Because you talk about how those using a synchrotron radiation or something.
Actually, that paper, Paul's journal published the original paper of the MOSFET structure, the device structure.
Okay.
And that's my collaborators, Arindam Ghosh, I cited. So they reported this particular structure and its device properties, and there are many other speculative claims that I flashed in one of the slides. that thought that the strain drives it into the metastable T phase. But what our results showed, no, it's actually more a game of moving the chemical potential locally under the device structure.
Okay, thanks very much. Thanks for all the explanation. It's a wonderful talk. So I give it back to the moderator.
Wonderful, interesting questions.
Yeah, that was just a lovely presentation and discussion. Thank you all so much. I apologize, my computer crashed in the middle of the introductions to the panel, but luckily I was able to come back. And now under normal circumstances, we could, walk across the stage to each other and hand you a plaque honoring you for this terrific talk that you gave today. And we'll hope to do that very soon. As I mentioned before we started the broadcast, I was supposed to be in Bangalore this month. So I'm sorry to miss you there, but hopefully there'll be another chance.
Sure, I'm sure we'll meet soon again.
Thank you and our panelists for today. Please do come back and tune in next week when we'll have Professor Anna Fontcaberta-Imoral with Jagadish hosting and another terrific panel. We have a lineup almost all the way through 2021 already. And so do keep coming back, and we'll look forward to meeting you online until we're ready to start to travel and see each other in person. And I think we'll probably keep doing this if Professor Alice Zhang's willing to continue to host every week. Thank you once again, and we'll see you next Friday. Thank you again, Professor Zhang.
Thank you, everyone.
Thank you.